Cloud infrastructure billing is notoriously opaque. Beyond compute pricing, a significant portion of overhead is a direct result of how data is physically structured. Platforms like Firebase and its real-time database calculate monthly bills by measuring two specific metrics: document byte size on the disk and egress bandwidth over the network. Standard NoSQL architecture binds structural schema, the names of every field, directly to the row data being stored. This creates what is effectively a JSON redundancy tax. When you write a document, string keys like user ID, timestamp, or active status are repeated redundantly across every single record. In a small test database, this overhead is negligible, but when multiplied across millions of dataset rows, that string key duplication inflates the total payload size. You end up paying a financial premium to store and transmit structural waste rather than the actual data your users generate. Firmly, treating schemaless architectures as inherently lightweight is a financial illusion that depletes operating budgets. To eliminate this bloat, we can use a strict, self-describing tabular architecture known as bJSON to decouple the schema from the data. As this diagram shows, decoupling the structural metadata from the row data strips away the dead weight, lowering Firebase write and egress costs by up to 50%. This transition shifts focus from server-side configuration tweaks to the internal mechanics of the data payload itself. The bJSON decoupling sequence begins by isolating the schema definitions. Instead of sending the fields array with every database write, the schema metadata is written exactly once to a central, highly cached Firebase node. This central node serves as the authoritative structural source for the entire database. As the schema cube locks into place, the client application automatically pulls the central document upon boot and caches it. This cache lives inside local persistent storage on the edge device, using mechanisms like SQLite, flat files, or Android shared preferences. The client engine immediately parses this downloaded schema document. It then constructs an in-memory hash map called the field map cache. Inside the device, you can see how this local cache translates string field names into zero-indexed integer offsets, mapping user ID to 0, username to 1, and email to 2. This precise mapping prepares the local system to resolve database reads and writes in constant O of 1 time, operating at lightning speed. The client edge now possesses the exact structural blueprint of the database. There is no longer any need to request or transmit schema data during ongoing backend transactions. Shifting schema awareness to the client breaks the redundancy cycle seen in standard NoSQL operations. This sets up step C of the protocol, the positional, values-only write phase. When pushing data to Firebase, the client completely omits the schema headers and named fields, transmitting only a flat positional array. We can calculate the exact byte weight difference. On the left side, stacking 1,015-byte string keys across a million-row database generates 15 megabytes of structural waste. On the right, bJSON writes flat arrays, dropping the structural byte weight to 0. Writing these flat positional arrays minimizes the byte size calculations Firestore uses to generate your monthly billing fees. Beyond storage fees, large NoSQL environments also suffer from transactional bottlenecks. High-throughput operations frequently hit limits caused by document-level lock contention. Traditional unified datasets force multiple independent workers to queue for write access on a single database node. To resolve this, the architecture relies on the multi-file database, or MFDB, federation model. MFDB breaks write blockages by decoupling unified datasets into independent entity file stores. These files are managed by a central master manifest, known as 104a.mfdb.bejson. This manifest acts as the central catalog, binding isolated tables like users, media, and pages together into a cohesive system. With this structure, independent workers read and write to dedicated Firestore collections simultaneously, without intersecting. This parallel I/O model means a heavy write operation on the orders table will not block reads on the users table. Avoiding lock contention directly reduces transaction retry costs and CPU burn. All the while, relational integrity is strictly enforced by the central schema manifest. MFDB Federation delivers relational database concurrency natively on top of flat file cloud collections. Before any of these parallel writes occur, The BE-JSON validation pipeline operates entirely on the local device. The schema validator acts as a strict gauntlet. As the visual shows, properly formatted arrays pass right through, while a bloated, corrupted element attempting to enter the pipeline is instantly rejected. This mathematical enforcement happens at the runtime level via standard Python, JavaScript, or TypeScript library implementations. Separating the schema from the data does not sacrifice safety. Local validation confirms structural compliance before any data enters the cloud network. These cloud write optimizations yield a secondary benefit: client-side RAID performance. Traditional JSON engines consume significant CPU cycles parsing string key hashes upon data retrieval. That dynamic hashing degrades mobile device battery life and slows down application rendering speeds. BJSON utilizes a zero-overhead parsing mechanism to bypass this problem. Pulling flat arrays back from Firebase skips dynamic string mapping completely. As depicted here, the local field map cache executes field evaluation via a direct, high-speed memory index offset, bypassing the slow, recursive hash lookup entirely. This results in constant O(1) memory resolution times on the client edge. BJSON transforms front-end applications into highly optimized rendering engines, completely free of structural processing debt. Deploying BJSON and MFDB architectures across a Firebase ecosystem strips away the artificial overhead created by legacy formats. Removing redundant keys allows enterprise applications to scale while maintaining a lean data footprint. Efficiency at scale depends on engineering the data format to eliminate waste at the physical layer.